So on Wednesday, we already started talking about neuro-rehab, and I didn't show you a stroke patient yet. So I thought about starting this presentation showing you a video of a stroke patient. Then we will go through reviewing the principles of motor learning and rehabilitation. And then we will enter into this topic, that is the application of sensory error manipulations to motor rehab, but also for evaluation and diagnostics. And we will cover also other types of patients, for instance, patients that are chronic users of cannabis, and also vestibular patients. So we start with stroke. So this stroke patient, which presents hemiparesis, as you can see, the left side of the body is showing weakness and a loss of motor control. So it's associated to a lesion in the right hemisphere of the brain of this patient. You can see that he's not able to use distal muscles with control. He's not able to open this jar. So it's compensating by using the other hand, as you can see, and placing the affected arm over the jar. So what happens with these patients? Well, as we were saying on Wednesday, just after the lesion, the patient is hospitalized, and very soon there's structural damage, which links to functional loss. So these patients start showing a loss in motor function, but also they may show emotional or communication problems. One side of the body may be paralyzed completely or partially, affecting the upper extremity or both the upper and the lower extremity. So after a first phase of hospitalization, the patient leaves the hospital and continues with treatment, with rehabilitation. And during the first around 3 months to 6 months after the lesion, they experience certain recovery, functional recovery. After that period, they stabilize, and there's no much recovery after that. But they continue training. For instance, in Spain, they keep on training, and they go to the hospital around 2 to 3 times a week, more or less, and they receive some therapy. And after 1 year, they do not receive any therapy anymore. Okay, they are absolutely discharged, and they stay at home. So, as we were mentioning the other day, there are certain rules that we observe in the pattern of recovery. Recovery seems to be proportional, because those patients that are more affected recover more, and also it is structured, so they recover more at the early stage post-stroke. Okay? After hospital discharge, there is a period of deterioration, and these patients reach around the same level of function they had 2 months post-lesion, around 5 years post-stroke. So there's a huge loss we call rehabilitation in vain. So it's a huge loss that also derives into readmission into the hospital. So this is what we are trying to solve. And this presents a number of problems. So first, everything we know right now, these patterns that I'm mentioning, proportionality, it's structured, most of what we know is based on clinical scales, okay? Clinical scales that are based on the observation of the clinician over how the patient moves. So there's a lot we don't know, and it may be because we are always using the same metric in order to understand how the brain repairs itself. We need to look at other metrics probably in order to find out how to solve the pieces of this puzzle. And also we need to improve our treatments, because right now the standard is occupational therapy in the hospitals, and there's no evidence, scientific evidence in meta-analysis that proves that this is actually more effective than nothing. So we need to find out which are the principles of recovery, which are the principles of motor learning, then design therapies that are effective, and design evaluation tools that allow us to explore the full puzzle in an objective way. And for this, I think that virtual reality is especially useful. And it mainly allows us to implement all these principles into controlled protocols in order to support the 3 pillars of neurorehabilitation, which is to provide improvement that is retained and that generalizes, so it can be applied to activities of daily living. At the end of the story, we want to help these patients to recover function in order to have a high quality of life. Okay, so we don't want them to be able to perform this game properly and be able to grab certain spheres. We want them to be able to brush their teeth or feed themselves, right? So generalization is a key issue. So for that, since, well, I would say more than 10 years ago now, we developed the rehabilitation gaming system. That is a virtual reality-based system for rehabilitation. The idea behind it was these patients do not receive enough therapy. They are discharged too early when they still can improve. So we need a system that is affordable, that they can even bring home and use it independently. And for this reason, we developed this system. So you can see that the interaction is quite simple. The patient is able to move his arms, which are captured by a depth sensor and mapped into the movements of an avatar. And in this way, he can interact with spheres. There are principles that are grounding the design of these protocols that we are defining. I will not get into detail in these principles, but because we already discussed them the other day. But this is a key issue for us. So we don't want to develop scenarios that are just for training, are motivating, and are fun to use. We want to understand how the brain works, how it learns, okay, and how it repairs itself. And then when we understand the mechanisms and the principles, we can bring those to design a therapy that is effective. So the key is in how the brain works. And for years, we have collected data using this system. And when we put all this data together, we can observe that there is this rule of proportionality and this rule of the temporal structure of recovery that pops up. And we also observed that while some literature has claimed that the structure of recovery is defined by a critical window that lasts between 3 to 6 months, we observe in our data that that's not the case. Beyond 6 months, these patients are still highly responsive to therapy. So it's our responsibility to give therapy to those. So if a patient is more responsive to treatment 6 months post-stroke or 1 month post-stroke, in comparison to 5 years post-stroke, it's our responsibility to provide therapy to that patient 6 months or 1 year post-stroke, but early at this period when their plasticity is enhanced and they're highly responsive to therapy. What we see in our data is that this critical window does not close at 1.5 years. And what we see in our data is that we don't know when it closes. So this is open. We don't know when the critical window closes, but we should profit from it. So this is the effectivity of our system when we use it in the clinic in stroke patients. But you can imagine that this system allows for combining it with other treatments. For instance, direct current stimulation. So this study we are running right now together with Ana Mura and in collaboration with Hospital Vall d'Hebron, in which we are recruiting stroke patients. We are exposing them to our therapy, the rehabilitation gaming system, and we're combining this with the stimulation of the surrounding area to the lesion using direct current. We compare two conditions, stimulation through direct current and sham condition, which simulates current, but there's no actual current. The feeling of it is exactly the same. So something very nice about this study is that it's double-blinded. The patients do not know in which condition they are. They do not know if they are receiving current or not. And the therapists and the evaluators also do not know which patients are being treated. Actually, it's triple-blinded because the therapist and the evaluator are not the same person and both are blinded. So in this preliminary analysis, in which we are including 5 and 7 patients in each group, what we see is that the recovery after only 2 weeks of treatment, combined treatment, it's already higher, as you can see in the mean value. in the direct current stimulation combined with the VR treatment. In the sham, only VR, it's a little bit lower. And also in the CAHI scale, which is a scale that refers to gains in the capacity of the patient to perform activities of daily living. For instance, using a towel or making a phone call. So we see that here the impact is already visible as well. So we are continuing to test more patients now. Also, we are running follow-up evaluations. So this is very good news. And this is quite promising. So we are not claiming that VR is a therapy that should be used in isolation and this is not. We should explore also how we can boost its effectivity using combined therapies. We can think also about pharmacology, in this case direct current stimulation. And another thing we are exploring, and I mentioned before, is the potential of this tool to capture improvement and to follow up the patient, right? So something beneficial about using the system is that we are collecting the kinematics of the patient continuously during training. And now this is not objective as I was subjective as I was saying before, as it happens with the clinical scales. I'm not looking at the patient and claiming, now it seems like this patient gained some range of motion. No, I'm actually using a camera, right? So everything is objective. What you see in literature is that they take all the kinematic data and then they extract descriptors, parameters. Okay, this is how it happens. So they say, okay, I'm going to quantify the range of motion of this patient in this axis, the speed, right? This Dimitar is something he knows very well because he has done his project in relation to this. So this is how it works. They extract parameters. And what we did is we thought, actually, if you analyze these parameters, if you extract speed or range of movement or different parameters of this type, descriptors, using different time scales, this may carry different information. So if we use a small time scale and we analyze these parameters at this time scale, we may be looking at information that is very different from the information we can extract from long or wide, big time scales, okay, large time scales. So we do that, and we observe an extra parameter that seems to be significant. That is 8 seconds window, okay, time scale of filtered hand paths. Okay, we apply a Gaussian convolution over hand paths with this window, and we see that at these 8 seconds, something is popping out, some information that relates very significantly or correlates with clinical scales, with the Fugl-Meyer clinical scales, that is the most accepted one. Actually, we tried many windows, okay? And that's why we found that at 8 seconds, something is going on. So we take this descriptor, that is how basically we call it total goal-directed movement, because it would represent hand paths with a time scale that is capturing voluntary reaching movements during play, during gaming. And we add it to our list of descriptors, okay? And now we say, okay, let's see if these descriptors are able to correlate to clinical scores. For instance, the Fugl-Meyer score. And we see that actually that's what happens. So we have many correlations here. Some of them correlate more, some others do not correlate, and we detect the ones that correlate the most. This is what is done in literature. But at this point, we would say, yeah, so we found 8 parameters that correlate with Fugl-Meyer, we are done. Well, that's the problem. Here's where most of the papers doing kinematic analysis in stroke finish. But the fact that a parameter correlates with a score does not mean that a change in that parameter correlates with a change in that score. Okay, it may not be the case. So correlation does not mean covariation. Okay, so this is what we do now. And surprisingly, we lose all significance for all parameters, except for the one that is the total goal-directed movements, which keeps being significant. Okay, and this is interesting because then you find out, okay, that's why the papers were finishing at this point, probably, and they were not looking at covariation. And covariation is very important because it talks about sensitivity. So the parameters, velocity, range of movement, jerk, all those do not covariate with the clinical score, okay? Now we ask the following questions. So, okay, this parameter seems to be sensitive, but can it capture proportional recovery rule, which Fugl-Meyer we know that captures, and can it capture the temporal structure of recovery? So we look at that. First, we see that both Fugl-Meyer scores are able to capture changes or improvement at the acute stage post-stroke, early stage, and at the later stage, chronic stage. Also, in our parameter total goal-directed movements, it occurs. When we divide patients in between mildly affected and moderately affected, it's also sensitive enough to capture improvements. And now we divide them by subgroups, by combinations. So which patients are acute and moderately affected or mildly affected, and the same for chronics. And what we see is that Fugl-Meyer is capturing differences between acute and chronics, which means that it's showing that there is a structure in time, okay? Acutes recover more than chronics, both at the mild, in the mild cases, and moderate affected patients. And in our case, we also, in the TGDM scale, so total directed movement score, we also are able to capture this sensitivity, so we are able to capture that recovery is structured in time. You may see that here, in the case of the mildly affected, it has not enough sensitivity to capture that is structured in time, that recovery is structured. So it's driven by the temporal structure of recovery, but we are not able to see that the TGDM measure captures the proportional recovery rule. So it's not sensitive enough to capture this. However, we are getting one step closer towards finding out other descriptors that can shed light into solving the puzzle. And I think this is what we should do in the field right now. We should explore the kinematics deeply and understand how the kinematics, synergies, and how the evolution of different descriptors are going to explain retention, are going to explain loss of function after discharge, and then we will be able to find out principles. So not only therapy should be guided by principles, but measurements should be guided by principles as well. Which brings us again to the puzzle. So one of the problems or the biggest problems of this puzzle, it's here, okay? Okay, we need to get closer to more reliable measurements, and we need to build more effective treatments. And what happens here? So let's imagine that we made it. We have the perfect treatment, they recovered. When they discharge the hospital, they are fully done, okay? And what's happening here? Will they lose this anyway? So we need to understand why these patients after discharge are not retaining those gains. Is the brain programmed to lose function? What's going on, right? So this is the next question. And here's where I will start talking now about error. So all the studies I'm going to show from now on are going to use error feedback in order to modulate stuff, to promote recovery or to assess recovery, okay, or damage. So what happens after stroke is that, as you can see, one of the limbs is not very useful. And what do we do? Actually, a healthy brain would compensate for it in different ways. It can compensate by adapting movements, or it can compensate by overusing non-affected limbs, right? So this leads us to a vicious cycle, the vicious cycle that we already discussed on Wednesday, or we mentioned on Wednesday. So if there is overuse of the non-affected limb, then the patient is not exposed to error, there's no learning, and the outcome, the future outcome of doing that action is poor. So this just reinforces loss, right? It's progressive deterioration. There is a way, the error here is important to understand that the error is having two effects. So on one side, the error is promoting learning because we learn from sensory error, but by the contrary, here is having a negative effect. Error is telling us, don't do that action again. Select another action. Okay? So error can favor learning, but also can be hampering learning. Because if we don't select that action, then we will not learn from it. We will not refine that action, right? So that's a problem that needs to be understood, because I'm going to based on this, I'm going to explain a number of studies that are grounded on this idea and trying to prove this double effect of sensory error. One way to reverse that vicious cycle and convert it into a virtuous cycle is constraint-induced movement therapy, which is actually standard nowadays. And you will find it surprising because first, it's a standard that can only be applied to 7% of stroke patients. It consists in placing a mitt or restricting the use of the non-affected arm. So these patients are forced to use the affected arm during 80% of their day, right? So they have to feed themselves, to have a shower using the non-affected arm, the affected arm. And as you saw in the video I presented in the first slide, that's challenging. That requires supervision, right? It's dangerous to do it without supervision. And if a patient is presenting emotional issues or depression, he cannot be prescribed with this therapy. And since it requires supervision, it's very expensive. So it's difficult to access this solution. But it seems to be quite effective in reversing this vicious cycle, because there's no action selection, right? They are forced to use the arm, they are exposed to error, there's learning, the outcome improves. So we propose an alternative to this, an alternative approach that could be beneficial to also those patients that are not suitable for constraint-induced therapy. We propose to reinforce the use of the affected arm instead of forcing it. Well, how? In virtual reality, we can manipulate error. We can reduce error. And if we reduce error, we will promote the future selection of that arm, because here action selection and learning are reinforcing each other. So to do that, we design a paradigm in which we are applying the amplification of the virtual arm of the avatar only when the patient freely selects to use the paretic limb. So we generate the illusion of function in virtual reality. And we design a task in which the patients have to perform certain reaching movements, freely using which limb to use. And we design 2 sessions. In the first session, they are just exposed for familiarization, and in the second session, we introduce progressively this help, this trick. We do it progressively so we keep them unaware of it. Actually, they were fully unaware of it, and many of them were confabulating about why they performed so well during the second session. Okay? They were saying, oh, today I feel full of energy, today is a good day. So they do an implicit attribution of this augmentation. But more interestingly, what we see is that the patterns of hand selection during the intervention are restored to normal. Okay, so they tend to increase the use of the affected arm spontaneously, only because we are tricking them visually, showing them that they are misfunctional again. And these changes are retained. Also, we observe in a sequential analysis that when they use the affected arm and they fail, the probability of selecting again that arm in the next trial lowers significantly. And this doesn't happen if they are not using the non-affected arm, only when they use the affected arm and they fail. This means that they are very sensitive to failure when using the affected limb. I do not have proof for that, and we would need to do more studies, or especially interviewing these patients. But I think they are doing an internal attribution of success when they use the non-affected arm, and an external attribution of failure when they use the non-affected arm. Basically, they use the non-affected arm, they reach something, they fail, the system sucks. That's it. Okay. When they use the affected arm and they fail, they feel, this is my affected arm, right? They think, this is my affected arm. I cannot do this with my affected arm. What was I expecting? I was expecting to fail. So of course I failed because I'm not doing it well, right? So it's a matter of how they are attributing success and error, which makes them contextually so sensitive to failure when using the affected limb. So based on these findings, we implemented a model. I will not get into detail, but it's composed by 2 units. So in this computational model, we are trying to solve how our brains select which limb to use in order to reach an object. And this depends on where is the object, right? So which is the cost that I require to reach that object, and which are my expectations of success when performing that action, which is based on history. Everything is based on history, even the cost I attribute to certain action. And for this reason, we have 2 modules, a motor unit that is computing the planning of the movement, and an action selection unit that is deciding which action is better to choose in order to optimize or reduce the cost and maximize the success possibility, the probability of success, right? But something I want to explain you, I will not get into this, then there is learning and so on, but what I want to explain you is how these neural nets that we coded here work, because later it will be useful. So these are direction-tuned cells, okay? Your motor cortex has direction-tuned cells to code many things, to code the direction of a target, for instance. For instance, now when I'm looking at that computer, some neurons in my motor cortex are spiking because the computer, if I want to grab it, let's say I want to grab it, it's at whatever, 90 degrees, okay? So some neurons are spiking more and some others are spiking less. If my computer would be at 180 degrees, sorry, it would be here then, then other neurons would be spiking more, not those that were spiking when the computer was 90 degrees. This is what we call direction-tuned cells. They are highly responsive to specific directions. And this has been found in monkeys and through recordings intracranial. And the activity of these neurons have been modeled as a cosine truncated function. What is this? So basically, a cosine truncated function defines that the neuron that is highly responsive for 90 degrees will be silent at 0 and at 180, and from there farther than that. Okay, so this neuron is highly active when the target is at 90 degrees, and then progressively less active until it reaches plus minus 90 degrees, and then is silent. And this is how these neurons seem to activate. Okay, this is what we call direction-tuned cells. Something interesting about these cells is that they adapt very fast through neural adaptation mechanisms. So if now you present me a target at 90 degrees repetitively, and you record all the activity of my direction-tuned cells in motor cortex, you will see that they start changing their preferred angle. Some that were showing high activity at 70 degrees will start being more active at 90 degrees until they are highly active at 90 degrees. This is useful because you have limited resources of neurons in your brain. So if you would be always exposed to the same location, the same direction, you want to recruit more neurons to code that direction. And that's why through neural adaptation, these neurons that were preferring other angles start being tuned for those angles that are presented more frequently. Okay, this has been reported in literature in the last 10 to 15 years in monkeys. And this is how we implemented this model. So after implementation, we simulated different types of treatment. And what we see is that after certain training, we can remove some of these direction-tuned cells. And we decide arbitrarily to remove those that are in between coding or preferring angles in between 0 and 90. We kill them, we delete them, okay? Now we observe how the system or the model is selecting which limb to use, and we start seeing learn non-use. We start seeing that the model doesn't want to select the affected arm for reaching targets that are appearing at this direction, because it has no resources to code properly those directions for planning movements towards them. So after treatment, we combine different possible treatments. So let's say that here we simulated a stroke patient, and then we can expose this patient to forcing the use of the affected arm when targets appear at those locations. Or we can just reinforce it. So when the paretic arm is selected by the model, we reduce the error, so we trick the system. And the combination of these different therapies seem to be affecting this reorganization of direction-tuned cells in a way that you see that the hole that we created in between 0 and 90 degrees is restored, okay? So these cells changed their tuning, changed their preferred angle in order to cover those directions that were lost in order to encode them, right? And we see that here, a mixed therapy seems to be quite balanced by the end in the distribution of direction-tuned cells. This mixed therapy is combining forcing with reinforcing. And here's where we thought that it could have some potential for recovery long term. So we went to the clinic and we tested we tested two groups, an experimental group and a control one. Both were exposed to virtual reality treatment, and the experimental group was also reinforced through this augmentation of arm movements that I described before. And what we see is that long term, the effects are promising. So we replicate that they tend to use more the affected arm. They are highly sensitive to failure when using the affected arm. And in clinical scales, it shows that at follow-up periods, the group that was tricked or reinforced, it's showing greater recovery. Okay, so at this point, I would like to think I convinced you that manipulating the error may have an effect in learning, may have an effect in recovery, and has an effect on action selection, okay? But it's not clear. You would say, well, I'm convinced about the action selection. These guys are selecting more often the affected arm. What do I have? A mosquito or something. So these patients are selecting more often the affected arm when you are providing this trick, but I'm not convinced about the learning. And I understand that. Because when we diminish the error, aren't we hampering learning? Shouldn't we be learning more the bigger is the error, the more obvious is the error? That's a fair question. That's actually discussed right now. And there are different approaches. So the more classical view is that the bigger the error, the more we learn. Okay, this is the classical view. But recently, Ersfeld and Schadmer showed that it may not be that the bigger the error, the more we learn. It may be that we learn more from those errors that repeat more often, those that are more frequent, right? And it makes sense if you think about it in functionality terms. So imagine that we are trying to shoot towards a target, okay? And we are shooting and we are making a plus 10 degrees error, minus 10 degrees error, plus 10 degrees error. Now we shoot and we have plus 90 degrees error. Maybe we don't want to learn from that, because maybe it's due to external factors. So maybe we should not do an internal attribution of that error, because it only happened once. So how is our brain dealing with this problem? Actually, Schadmer's solution, that is, how much we learn from an error depends on how frequently it occurs and which is our history of exposure to that error, would solve that problem, actually. So based on that hypothesis, we develop an experiment in which we combine, in this case, a head-mounted display, so it's an immersive, interactive VR scenario, with an exoskeleton for tracking arm movements. And we apply different manipulations to the error. Okay, we have three conditions. The M plus condition, here, in which when reaching towards the target, we diminish the error. Okay, so it's related to the trick we were describing before. This would be reinforcing using that action again, right? So it's diminishing the error. M minus, it's a negative mapping in which we are amplifying the error. And NM is a neutral mapping. So if you think about, if we are able to apply this, then these three conditions, what we would see is that in the M plus condition, these patients did very small errors very frequently. Okay? While in the M minus condition, when we're augmenting the feedback, the visual feedback of the error, these patients visualized more large errors and less small errors. So this is actually what happened. Okay, let me describe this. So first, so this is the paradigm, just to mention that we were adding perturbations on top of that. Okay, we were adding scheduled perturbations towards the left and the right, 30 degrees plus minus. So we do this, and it's very often done in this type of paradigms, because we want to measure learning or adaptation on trial basis. So these patients are continuously experiencing a visomotor rotation towards one side, the other side, one side, the other side. And first, we are showing smaller errors, so working as an attractor, we're diminishing the feedback of the visual error. Then it's neutral, and in a last block, we are augmenting it. A second group will go through the same conditions, but in reversed order. Okay, we did this just to counteract any order effects. And what we see is that first we were able to manipulate the frequency of exposure to error through this method. In the negative mapping condition, you can see that the frequency of exposure to zero error or small errors is lower than in the positive mapping condition. Okay? So we can alter the distribution of errors to which we are exposing these users. And if actually we learn more from those errors that we're exposed more frequently, what we are doing here is programming people to learn from the errors we want, right? Here we are programming people to learn more from big errors, because we are creating a history of visual errors in their brains, right? We are creating a memory of large errors. Here we are not creating memories of large errors. We are enhancing memories of small errors. So if we learn more from those errors to which we are exposed more frequently, then we should see that here people is learning more from big errors. Here people is learning more from small errors. And think that this is the same people going through the three conditions in different order. Okay, so it's not two groups, but it's within subjects. And this is actually what we found. So you can see that in the positive mapping condition, in which they are exposed more frequently to small errors, learning from small errors is significantly higher. So you can see in comparison to the blue, in which we are augmenting errors. Okay, but it was so beautiful, this plot, that we thought we may be doing something wrong here. So maybe it's an artifact, we don't know what's going on, but it's so beautiful. And then we thought, okay, we have the neutral mapping condition. So we have people who we programmed for learning more from big errors, and then we're in neutral mapping where we did not apply manipulations. And we have people who were exposed to highly frequent small errors, and then we're exposed. So let's look at the neutral mapping. Let's compare both groups during the neutral mapping condition. So this is what we do now. And as you can see, first initially we didn't see anything, okay? Each block was 150 trials. So we divided the neutral mapping block in two halves, the first half and the second half, and the effect popped up. So it's very interesting to see that those that were exposed to small errors, now they are learning highly from small errors. Group 1, which was exposed first to small errors. And then the group that was exposed to large error is learning more from large errors. But this is not significantly different, maybe because we are lacking power. But the trend is here. And during the second phase, the second half of the block, this disappears, which is actually makes a lot of sense. Because if we learn more from those errors to which we are exposed more frequently, we are talking about a highly plastic, rapid adaptive mechanism. So it should not be present for a long time. Okay. And this is nice because Ersfeld and Schadmer introduced in their model this hypothesis which we are proving. They said, in our model, we are predicting that meta-learning vanishes when a small delay or gradual washout alters the history of errors, demonstrating that savings depends crucially on the memory of errors that is accumulated during training. And we are showing how transient this modulation is. Okay, but which are the mechanisms supporting these memories? So where are we storing our memories of visual errors? Interestingly, recently, this paper from Ersfeld and Schadmer showed that in monkeys, intracranial electrodes recording the activity of Purkinje cells in the cerebellum are showing some relation to, or maybe encoding those memories. So what they do is, and now I want you to remember the story of the direction-tuned cells with cosine truncated function for activation, okay? Because what they did is they said, okay, so in the motor cortex we have these direction-tuned cells. What about cerebellum? Let's record a lot of single Purkinje cells in cerebellum. Let's expose monkeys to follow a target with their eyes through saccadic movements. Let's measure error, and let's see if at the population level these neurons are actually direction-tuned neurons. If we interpret the activity of these neurons as direction-tuned neurons and we try to decode it, maybe we are able to find out the encoding of the visual directional error. And this is what they got. So they found out that from Purkinje cells, they are able to decode visual directional errors in ocular movements. Okay, so it's a good candidate for storing memories, because direction-tuned cells, as we saw before, can rearrange rapidly through neural adaptation. So based on this hypothesis, we also see that the endocannabinoid system, which is highly present in cerebellum, is regulating all the inputs to Purkinje cells. Okay, and it's not only that, but this endocannabinoid system has shown to be highly to be highly related to Purkinje cells activity. For instance, in 2005 already was shown that exogenous endocannabinoid intake of exogenous cannabinoids, synthetic, lower the number of spikelets of Purkinje cells. In humans, this was in animals, but in humans, eye blink conditioning, the acquisition of conditioning in an eye blinking paradigm, as you can see, is slowed down in cannabis users, in chronic cannabis users, which are in abstinence, 24 hours abstinence. And here also we recently published with Hospital Clinic a review in which we show that there is some evidence, if you put it all together, that cannabis users are presenting symptoms related to cerebellar alterations and malfunction. So our hypothesis here is, could it be that memory of errors is located in or encoded in this direction-tuned Purkinje cells, which are triggered or depend on the correct functioning of the endocannabinoid system? If that's the case, it would be very interesting to study implicit learning, which depends highly on visual error and prediction errors, on cannabis users. And here is where we went to test cannabis users in Hospital Clinic in the addiction unit. And we designed a paradigm which was actually previously reported in literature, that consists in moving a pen over a table, moving it towards a target, okay? So participants start at a home position, and then a target that could appear all around it lights up. So targets can appear at any of these positions. After holding the home position for a while, target lights up, and then the participant has to go and overshoot the location of the target and then go back to the home location. So it's a very simple task. What makes the task more interesting or challenging is that after certain period of training, we introduce a visomotor rotation, 45 degrees. So when the participant is moving the cursor towards the target that lights up, he actually sees the cursor moving towards the adjacent target on the right. And this is confusing. After 2 trials, we stop the task and we say to the participant, look, we are tricking you, we are sorry, but I'm gonna tell you a trick, okay? From now on, go to the target that is on the left of the target you want to go to. So aim at this target, and since we're applying a 45 degrees and they are separated by 45 degrees, you will see that you counteract this manipulation that we introduced and you will perform perfectly. Just after you say that, the participant can do it perfect. So goes with 0 error degrees, goes to the target, okay? But then something interesting happens. And it's that even in healthy subjects, you can try it yourself in this task. We have it in the lab if you want to experience it. You start growing an error, okay? You start following the rule, going to the neighbor target, and suddenly you start accumulating an error, but you don't understand what's going on. You think they are tricking you again, and the visomotor rotation that was applied is changing, but it's not changing. The thing is that our cerebellum is not going to stop learning, okay? You explicitly know that you are doing well and you don't want to learn more, but your cerebellum is finding a mismatch, it's finding an error. Implicitly, you are aiming towards here and the cursor is moving towards here, right? Even if you are compensating explicitly using the strategy. There is a 45 degrees error that is going through your eyes, reaching your cerebellum, and your cerebellum is adjusting the mapping. It doesn't matter that you don't want to learn. Let's call this, I like calling it involuntary learning. So it's a task in which you can measure involuntary learning. It's very implicit from the cerebellum. So this is the task. Okay, I didn't remember I had the video. It's very simple. This is baseline, just reaching to target. Now we introduce the manipulation, and you will see now, okay? So it's very obvious. So these are the results from healthy subjects and cannabis, chronic cannabis users. So the black line is healthies. So you can see when first there's baseline, we introduce the manipulation, 2 trials, wow, what's going on? We tell the trick, the strategy is applied, it goes back to normal, and then it starts growing here in this low, as you can see. But the cannabis users show it below this curve, so they are slowed down in their adaptation. Interestingly, when we take out the visual feedback, and we do not provide visual feedback at all, both groups perform equally, okay? So these participants are not having issues in applying the strategy to compensate the manipulation. They are able to apply it here very fast and 0 error forever. But if you give them visual feedback, the cerebellum cannot stop learning, okay? There is a mismatch, there is a prediction error. So this proves this difference here between controls and cannabis users, or suggests that cannabis intake, chronic, and in this case during abstinence, so they are chronic cannabis users, may lead to alterations in implicit learning, and which may be related to cerebellar malfunction or damage. And what makes this interesting is that we found out a method that we could call, it's able to detect behavioral metrics of cerebellar damage. So if you talk with clinicians in addiction units, they will tell you that cannabis users have no problem with the cerebellum, okay? But in this task, we are able to capture a subtle damage in their cerebellum, which is presented through their performance in an implicit learning task. And at this point, we thought, okay, so that could be useful, because vestibular patients actually may not be diagnosed with any cerebellar damage, but we could be finding out that they have some subtle damage that we cannot capture with clinical measures. And why we thought about this idea. So, okay, I'm going to explain how the vestibular system works a little bit, and maybe I have 10 minutes or so. Okay. So, the vestibular system is formed by a peripheral part and a central part, okay? So, the peripheral part, which is located in your inner ear, is composed by hemicircular channels and tiny organs. And all of this is partly covered by hair cells, okay? And these hair cells transform mechanical forces into action potentials. And these action potentials are then processed at central vestibular or the vestibular nuclear complex to extract information together with other areas of the brain, okay, about your head motion and to compensate for this head motion. So this central vestibular nuclear complex is sending or is projecting into cortex, parietal, thalamus, and also cerebellum, okay? So the vestibular ocular reflex is triggered by all these mechanisms to compensate for head movements. For instance, if you are turning into a wheelchair, okay, and you want to read, you will be able to do it. And that's magic. That's the magic of the vestibulo-ocular reflex, okay? This mechanism is able to trigger ocular movements reflexively, which counteract your head movement very rapidly. So you can maintain the image in your retina, in the center of your visual field, and you are able to read. For instance, this is a test that shows the vestibulo-ocular reflex. This person is in complete darkness, is not able to see anything, but there is leftward rotation, and you see how his eyes are compensating for the movement, turning towards the opposite direction. Okay, this is a reflex, everything is working, this is good, this is useful. What happens is that when you have damage in your vestibular system, this does not occur. It may even occur when you are not turning. And this leads to vertigo, nausea, and for these patients it's really, really difficult to keep with their lives. So something is going on that is not allowing them to process vestibular information and to compensate for it. But this lasts very, very short. Like after 3 months, these patients most of them are fine and recovered. Why? Because all these structures I talked about that communicate with the vestibular system are able to compensate for it. For instance, cerebellum is playing an important role in there. However, some of these patients do not recover. And we do not understand why they do not recover. But we have to understand the full system. Because when you talk with a clinician and they describe the symptomatology of vestibular patients, they often attribute it to the vestibular system, but it may be associated to damage in other areas. So together with the Hospital of Tarragona, Joan 23, we started a study in which we hypothesized that those patients with vestibular damage, even if it's peripheral, that do not recover after 3 months of training, may have damage that is not diagnosed in other areas. And a good candidate that would explain lack of adaptation to the vestibular loss, or, well, vestibular, let's say, malfunction, it's cerebellum. So, based on this idea, we hypothesized that these patients, which become chronic may have difficulties to perform the task I described before, to adapt implicitly. So if they cannot adapt implicitly to correct for visomotor rotations, it may be that their cerebellum actually is not working well. So we recruit patients at what we see. This is also a paper in preparation. Actually, it's an ongoing study that we conducted together with Annabelle Munt, that is a student that was collaborating with us last year. And we are here only presenting preliminary analysis from 4 patients in the vestibular group and 7 controls. So it's very few subjects. And as you can see already, the difference between the controls and the vestibular patients, it's huge, right? So vestibular patients are able to apply the explicit strategy, are reaching towards the neighbor target, and are able to counteract this visomotor rotation, but their cerebellum, that should be involuntarily learning, it's not learning. Actually, vestibular patients here are performing much better than control subjects in this task, because they are not learning when they do not want to keep learning, right? So you can see that they are stable at 0. These are medians, and these are only 4 subjects. We are now collecting more data, but as you can see, the results are quite clear. So why this is useful? Well, because if actually those patients that do not recover after 3 months are not recovering because of cerebellar damage that is underdiagnosed, we can predict which patients will not recover, okay? And we can know where is the problem, and we can act on it. So just to summarize the different points we have touched, first we talked about how virtual reality shows potential for principles-based treatment, but also evaluations and metrics. We have talked about how reducing error magnitudes promotes use. Based on a model, reinforcement-based therapy seemed promising. We tested it in a longitudinal study, and we found that reducing error magnitudes also may promote motor recovery long-term. When we explore whether we learn more from big errors or small errors, we find out that we learn more from those errors that are present more frequently, which means that reducing error magnitudes and centering them around 0 degrees should not be should not be a problem if we want to apply this principle for recovery. Actually, the most effective way to go for learning would be to provide highly frequent sensory errors centered at those errors that we repeat more often, right? So at those errors that we want to correct rapidly. So we can use this principle to speed up adaptation. And finally, we found out as well that low implicit adaptation rates are present in chronic cannabis users, may indicate cerebellar alterations, and also may allow us to predict the recovery of vestibular patients. So thank you very much. I just want to mention to finish that this is a work, like this work has been done in collaboration with many institutions, IBEC, as you know, Iodine, Hospital Vall d'Hebron, Del Mar, Joan 23 from Tarragona. So just to mention that this is a huge collaboration with clinicians and other partners, also Saddle Point from UK. Yeah, thank you.